So, welcome back again, and in this lecture, in the previous lecture actually we discussed black body, the characteristics of the black body. We talked about absorptivity and emissivity of the black body and different bodies compared to the of a body compared to the black body, and we discussed that black body actually is a kind of perfect emitter and perfect absorber, and it emits its energy according to the temperature that it's the temperature of the body itself. Okay. Yeah. So, in this lecture what we are going to do, we will discuss two laws more. One is Planck's law, not two actually, Planck's Stefan-Boltzmann law, and then last one will be Wien's displacement law and some of its application. Okay. So, what is actually Planck's law tells? So, Planck's law is actually describes the amount of radiation emitted by a black body. So, now there are very important things here. We already have assumed that the body that we are considering is at a temperature, whatever the temperature, okay, and then how much is the and this is also called brightness. Sometimes we will see this one. If you just remember, in the previous lecture we saw that the radiance that we actually measure, that the what you call this radiance that is measured by the I am missing whatever that the radiance that is measured by the satellite, sorry see this. So, the radiance that is measured by the satellites, it's actually given by the Planck's law, and that's how Planck's law can be related to the brightness of the temperature of the any planet or any surface or any star, and this is the actually given. So, this is this Planck's law describes the amount of radiation that is emitted by a black body at each wavelength as a function of temperature, and this is actually, so its only variable here you see is actually temperature. What you see, you have this function E is equals to h nu c nu cube upon c square 1 upon exponential h nu upon k t minus 1, this value you have. Okay. And if you see here, this is a little complicated equation because the temperature is here in the exponential and it is in the denominator, and you have to subtract 1 from there. So, if you see the spectral radiance of the surface of the black body, and what will be the absolute temperature, it is given in the Kelvin. Nu is the frequency of the emitted radiation. Here the K is actually Boltzmann constants. You can just, there are so big numbers, we usually just write 1.38 into 10 to the power minus 23 meter square per kilogram per second square per Kelvin. This unit can be converted into joule, because energy, you just remember here E is equals to kT and energy is actually joules, or so you can calculate the what will be the unit of E K here, okay, joules per second temperature. And then you have like Boltzmann constant, this is given by this, and then you have H, which is Planck constant. We usually remember 6.63 into 10 to the power minus 34. If you have to remember this one, you just remember 6.63 10 to the power minus 34, okay, meter square per kilogram per second, and c is the speed of the light, which is actually 3 into 10 to the power 8 meter per second. So, in this equation if you see, there is only one dependent variable, and that is temperature. If you remember, we have been talking about the black body, that radiation is dependent. If you remember the previous lectures, we talked about that the radiation that is emitted by the black body is only dependent on the temperature, its temperature. So, in principle, you can, if you can measure the energy that is emitted by the black body, you can correlate that with the temperature, or you can see this one Planck's law. Okay. For example, if you see here, so you have irradiance that is plotted here, okay, and because the unit you can see watts per meter square per nanometer, and maximum is somewhere around 2, it is peaking around 0.5 or 500 nanometer, and this is at the top of the atmosphere. In the surface, part of the energy will be absorbed, so many of the energies will be absorbed here. So you will have, and then you will have several absorption bands here, because in the surface, in between the atmosphere and the surface, there is a huge gases that are present, and some of the gases will absorb the radiation, okay. And if you just see, another curve is given at the below 10 meter below the ocean surface, so it will be further lower. You see this one, it comes here. So this is very important phenomena that you can use, and if you can see these absorption bands are wavelengths. These can be used to characterize the presence of the particular species that is there. Now, if you see here, what is plotted here is spectral radiance, okay, and this is kilowatts per steradian per meter square per nanometer. So now you have to see this one. This is, remember here, this is radiance actually, because the per steradian comes here. Here the equation was given as a radiance. Here the plot is given as a spectral radiance, and if you see here per unit wavelength here, and if you see that you have a body, classically if you see in a classical, according to the classical theory, if a black body has a temperature is at 500 Kelvin, what would be the maximum temperature that, or what would be the energy emission pattern, you can actually do this one, and this deviates from hugely from the what we have actually observed. And for example, we have 5000 Kelvin, this radiation is somewhere around here, you know, and if you, and in 4000 Kelvin you have, it is peaking somewhere around here. At 3000 Kelvin you have much flatter and then peaking somewhere around here, okay. One thing is very important here, this law, you can see the spectral dependence of energy emitted, spectral dependence, because spectral means we are talking about the wavelength. So this is a spectral dependence of the energy emitted by black body at different absolute temperatures of the black body, just you have to remember. Now what you see here, one thing that you can notice here, that as the temperature of the black body becomes lower, the wavelength is shifting right, or wavelength is increasing, okay. As the temperature, what is happening, as the temperature is actually reducing, wavelength is increasing. This is very important, and this we will see the peak wavelength. I mean, I am saying that the lambda max at which this peak will be there for the emission, and this is actually we will see that is called Wien's law, or Wien's law of displacement, okay. So the Stephen, before this one, now we will have Stephen Boltzmann. So Planck's law is actually very important. It actually tells about the spectral behavior of the emission of the radiation from a black body, and we have seen, and as from the equation you can also see that this emission is actually only dependent on the temperature, okay. And the Stephen Boltz's law is one of the very foundational principle of thermodynamics and electromagnetism. So it can thermodynamics is because of the energy, and because here the electromagnetism, because we believe it was there that electromagnetic radiations are actually nothing but they are they will have a, because of the movement of the ions and then electromagnetism will be there, and this describes the relationship between the temperature of an object. This object need not to be a black body here, just remember, but most of the time this equation will work when we consider them as a black body, and the total amount of radiation it emits. So temperature, there is a relationship between temperature and radiation. So what is that relationship between this one? This is governed by the Stephen Boltzmann law, and this was named after two physicists, Joseph Stephen, who first derived the law empirically in 1879, and Ludwig Boltzmann, who provided a theoretical explanation in 1884. And this is their actually, because of their both the names, they were actually given by the Stephen-Boltzmann law. And this is a simple equation. The amount of the radiant energy emitted by a black body. Again, now when you say black body, this means this epsilon becomes 1, emissivity becomes 1. It is completely emitting all the radiations, all the wavelength, is proportional to the 4th power of absolute temperature. So, absolute temperature means the temperature will be in Kelvin. This is very important. Okay, and T when we write is actually Celsius degree centigrade plus 273.15. So, if you have to add whatever the temperature you have, you add here, then it will be temperature will be given in Kelvin. Okay. So, this is the absolute temperature, and the 4th power of the absolute temperature means T to the power 4. Okay. So, this is proportional. So, this means E is proportional to the absolute temperature and 4th power of the absolute temperature. So, when you have to put this one, actually you can put this, remove the epsilon, this will be epsilon sigma T to the power 4, and this is actually for the black body. When you have a non-black body, this equation will becomes E is equals to epsilon sigma T to the power 4. This is non-black body. So, you have to consider one term here, one extra emissivity you have to consider here, and then sigma is nothing but 5.67. It is a Stephen-Boltzmann constant, because you have to remove, when you have to remove proportionality, you have to put this one, and this is actually called as a Stephen-Boltzmann constant. Okay, you remember this is a Stephen-Boltzmann constant, and sigma is given by this value 2 pi to the power 5 small k. K is here actually Boltzmann constant. 15c is divided by 15c square h cube, and if you just calculate this number, this turns out to be 5.67 into 10 to the power minus 8. Just remember this much, and remember the unit watts per meter square Kelvin to the power 4. If you don't remember the units, I will tell you very perfectly to remember, because energy is actually in watts. Just remember that energy is in the watts, and you have T to the power 4. Okay, watts per meter square, sorry. Energy here is actually is a kind of flux, it is a flux. Okay, radiant energy or flux density or radiant flux density. So, you have a flux here, and this will be actually sigma. Okay, so I don't know the unit of the sigma, and it will be T to the power 4, means here you have Kelvin to the power 4. So, just see the unit of sigma will be watts per meter square Kelvin to the power 4 minus 4. So, this is how you should remember the units. Just don't try to remember everything, but rather than you try to calculate this one with what you call with the remember, you try to remember the equations and then some of the units which are very easier. So, otherwise your brain will be fogged, you will be like you don't remember, you will confuse with the units. So, don't remember all the units, remember very few units and remember the fundamental equations with that, and then you can just you can see what the unit will have. And if you just see this E, area under curve, and because we have talked about E is a function of lambda. Okay, we remember it one. What was this one? Radiance or irradiance? It was irradiance. So, irradiance or radiant flux was per unit wavelength. So, you have here wavelength and you have E or irradiance. Okay, watts per meter square per nanometer, and you have lambda, say example in nanometer, and you have some peak like this. So, what you can calculate again this one. So, the total energy will be given by E lambda and integrate over the wavelength. Wavelength can vary from 0 to infinity or whatever the maximum wavelength you have. In principle, you can have infinite because this is a continuous spectrum, but you have to somewhere at some point of time you have to truncate the value. So, important implication of this one, temperature dependence. So, this means the energy radiated increases significantly with the temperature. This is because energy radiation of the energy varies T to the power 4. So, if you just double the temperature, the radiation energy or radiated energy will be 16 times 2 to the power 4. Black body behavior, it described idealized radiation of a perfect black body, and this serving as a reference for real world object. So, this is also serves as a reference for the real object. And then thermal equilibrium, you have to always consider this one, that objects in the thermal equilibrium with their environment absorb and emit radiation according to the law. This is, so first thing you have to very careful that here you have to see that the object that we are considering, it has to be in thermal equilibrium with the environment that is absorbing or emitting the radiation, and thus achieving the balance of incoming and outgoing radiation. We will see the equation, this one between the earth sun energy balance. So, we will see this one, and if you just talk about this one, this you can also extend energy balance in the universe, not of our topic, but this is Stephen Boltzmann law is fundamental to understanding the energy flow in the stars, planets and other celestial bodies. So this law is really very powerful, and it's very simple. Sigma E is equals to sigma T to the power 4, but it has lots of application, and it has application in the astrophysics, it has in the climate science, you have thermal engineering. So, everywhere astrophysicists, I don't know much about this one, but they have application like so stellar luminosity, stellar classification, then what is the total power, their energy, the power that is actually output is given in the luminosity, and which is actually with respect to sun's temperature, and that is how the stellar classification, different kind of stars have been classified with this luminosity itself, actually the total output energy. And then climate science, we talk about energy earth balance budget, we have talked, and we will specifically come back again here. And this is the earth's temperature that is modeled by the balancing incoming solar radiation with the outgoing infrared radiation that is emitted by the earth's surface. So, this the energy that the radiation that has to be in equilibrium between the incoming solar radiation from the sun and outgoing infrared radiation that is emitted by earth's surface. This is also helpful in understanding the greenhouse effect after earth's radiative equilibrium, because this is where we got the clue that if you just assume earth's energy balance, the temperature would have been minus 19 or degree centigrade, so which is about 35 degree centigrade lower than that what we have observed. And this is where we actually discuss that this also gives a clue that there is some other things that is actually absorbing the radiation in the in the earth's atmosphere, and that's why the concept of greenhouse gases came here. Then you can also, this is also used in thermal engineering, like heat transfer and designing of the furnace. The last one is actually Wien's law. So, the Wien's law or Wien's displacement law, both it is said, and this is named after the Wilhelm Wien, and that was derived in the year 1893. This states that black body radiation has different peaks of temperature at wavelength that is inversely proportional to the temperature. So, what is there? So, it says that black body radiation has different peaks of temperature. So, you have T max and you have wavelength actually lambda. So, for this one, for maximum temperature there will be 1 lambda maximum at which they actually, and they are actually inversely proportional. And Wien's displace, and then there will be actually this is again. So, you have actually temperature is proportional to 1 upon lambda. This means lambda max, if you want to put lambda max into capital T is equals to constant, and this constant is usually known as Wien's displacement constant. So, if you remember in the previous slides, I told that hotter the object means higher the temperature, lambda max will be lower, because this has to be constant. So, if the temperature becomes high means it is hotter objects, the lambda max will be low. So, hotter objects will be emitting at the lower wavelength, peaking at the emissions at the lower wavelength compared to the same object which has a temperature lower, and that will be peaking little higher wavelength. So, this is the physical constant defining the relationship between thermodynamic temperature of the black body and the wavelength, which is known as Wien's constants. It is the product of the temperature and wavelength of the black body. So, lambda m into T, this is constant, and we will see this one. Yeah, so this is very simple equation. Again you have, so there is a inverse relationship between wavelength of the peak of the emission of a black body and its temperature, and when it is expressed as a function of the wavelength. So, this less powerful consequence is also known as Wien's displacement law. So, lambda max into T is equals to B, which is constant, and the value of B is equals to 2.98 or 2.89, or usually we take 2.9 into 10 to the power minus 3. Now, again you remember that what will be the unit of this one. Okay. So, lambda m is actually here is in say nanometer, okay, and temperature in Kelvin. So, this unit will be having actually, or if you want to write meter. So, Kelvin if you are writing, then it will be having meter Kelvin. So, the Wien's constant is actually 2.9 into 10 to the power minus 3, okay, meter Kelvin, and capital T is the absolute temperature of the body, and this is actually a huge number is given, but you can just remember truncate any place. 2.9 will be there here, if you truncate it will be 2.90. So, just you can write 2.90 until and unless you are very concerned about the exact numbers. Okay. Yeah. So, this is very important. I gave that one. So, you just remember lambda max is T is equals to 2.9. You can see straight away write this equation. So, hotter objects means T is larger, they emit most of their radiation at shorter wavelengths. This means lambda lower, and that is why they will appear to be bluer, and that is why they appear to be blue, because lower, we remember that the sun radiation is peaking around blue wavelength around 500 nanometer. Cooler objects means temperature is less here, okay. So, this will emit most of their radiation at longer wavelength. So, this means lambda will be higher. At any wavelength, hotter object radiates more energy at all wavelengths than a cooler one. Obviously, this is actually hotter object will radiate more energy, because this will be given by sigma T to the power 4. So, if you have a hotter energy, it radiates more energy at all the wavelengths, not only a specific wavelength, but it will be at all the wavelengths. And if you see this equation, this is the intensity, okay, that is plotted, and you have a different wavelength, ultraviolet, visible and IR, and for example, this is the case of our sun, okay. You remember this value somewhere around 5800, or sometimes you will see 5900 Kelvin, or sometimes you will see 6000 Kelvin. So, do not worry about that, just remember. So, this will be peaking somewhere around here, visible, in this one. And then if the temperature is a little lower, this peak max, lambda max will shift here. Then if you are again temperature is 4000, this lambda max will shift again, and 3000 lambda max will be higher. So, if you compare, and if you just, for example, in the objective questions what is given, this curve is given, and it is not given that what is the temperature, absolute temperature. For example, this one it is not given, you have given lambda max, then you can readily see this will be, if you do not see it exact, remember the number, you can still calculate that one. And this is actually a few known object examples we have given here, like you consider a star that is emitting at 15,000 Kelvin, sun which is emitting at around 1500 Kelvin, and another star that is emitting at around 3000 Kelvin. one human that is emitting about 310 Kelvin. So, you can see that how much would be the wavelength. So, you just remember this one, lambda m into lambda max is T into is equals to constant. So, this means 2.9 into 10 to the power minus 3. So, 0.029 you can write, and if you see the black body, this is temperature, then lambda max is given, and this is in the meter, and if you calculate in the nanometer. So, a star which is at 15,000 Kelvin, it will be giving maximum energy at 193, which is actually in the UV region. The sun that we talked about is about 5800 Kelvin, it will be peaking somewhere around 500 nanometer. So, you can just see this one, it will be in the visible, and this is actually a blue wavelength. If you the other star which is about say 3000 Kelvin, it will be giving around 960 nanometer in the IR region. So, it is like 1 micrometer. And if you talk about the earth, which is about 288 Kelvin, 15 degree centigrade global average temperature. So, to 288 Kelvin, it will be giving around 10,000 nanometer or 10 micrometer. So, this peak wavelength, if you just remember the emission from the sun, I gave the example of emission, comparison of emission, black body emission of radiation from the sun and earth, and then human body, which is about say 98.6 degree Fahrenheit or 310 degree Kelvin. This will be giving again in the terms of little lower, around 9.3 micrometer. So, when anything, if the energy is emitted in the IR region, it will be actually kind of thermal, you can thermally experience that one. So, this is very important equation, and key implication of the Wien's displacement law, color and temperature correlation we talked about, astrophysical application, then everyday observations like when it's heated metal glow red at lower temperature and whitish or bluish white at higher temperature. Even if when you are burning this one, your cooking stoves, when they are actually peaking at the highest, in the inside it will be looking like bluish, other side it will be yellowish and reddish. So, that kind of things are there. Yeah, so with this I think I have completed this different laws which are actually for the physical laws that are governing climate change. So, in the next lecture we will discuss about the actually thermal equilibrium between the energy that is emitted from the sun and energy that is emitted from the earth, and how they are actually in equilibrium in the atmosphere. We will try to calculate the temperature of the earth accordingly, and then some of the things like aerosol cloud interactions, and then we will finish this lecture, this course itself. Yeah. So, thank you very much.